So this is just section just about applying all this work we've done with logarithms and exponentials and applying them to word problem situations. And in calculus, you'll see a lot of different kinds of word problems that use some of these ideas. So that's why it's good to see them this year or this semester. So half-life, I don't know if you've ever taken chemistry. Half-life is how long it takes. Usually, it's a radioactive element to reduce to be half of what it was. So half-life is, so it's half. How long does it take for something reduced by half? So they gave us this exponential model, and they're asking us to find the half-life of it. Well, if I initially start with 100 of whatever of it, 100%, 100 grams, half of it would be 50. So I could think of this as, well, when is this equation equal to 50? Because I started with 100. Well, it doesn't necessarily have to be the 100 and the 50, whatever it is. When I know that this, whatever's left, divided by whatever we initially started with, that would be equal to 1/2. So for this one, we're going to divide by 100, but you could always just jump to this point where 1/2 equals e to the negative 0.036t. And now to unlock that exponent, as we've learned before, we're going to take the natural log of both sides. I'm going to use natural log because it's base e. So I have the ln of 1/2, whatever that is, some decimal, equals negative 0.036t. Because remember, ln and e are inverse operations. Taking the natural log of something raised to the natural base, those undo each other. So I'm going to divide by the negative 0.036, divide by negative 0.036. My calculator is telling me that the half-life is 19.254 years. Or days. No, does it say what it is? No, it doesn't give us the unit. But that's how long it takes to reduce by half. So for this situation, they're telling us the half-life is 8 days. Then they're asking us to find a couple things. Find the annual decay rate, and then how much will remain. Oh, we lost it. All right, well, I'm going to make up a problem. How much will remain after 10 days? All right, so to find that annual decay rate, now what you got to think back to is when we talked about exponential models initially, that was our b, that was our base, where it was the 1 plus the rate. Well, since this is decay, we know the rate's going to be negative. So I can do this. I can say, I know that, and you also know that y equals ab to the x, or ab to the t. I know if I'm looking for the half-life, I know the time is 8. The half-life, if I take y and divide it by a, how much there is now divided by how much there was initially, and if I know the half-life is 8 days, half of it's going to remain. So I can do that, and then I can take the 8th root of both sides, not third root, 8th root. And that will tell me my b number. In case you don't know how to do the 8th root on your calculator, one way to do it is just to take 0.5 and raise it to the 1 divided by 8, right? Because the fractional powers, fractional exponents situation. My calculator is telling me that the b number is 0.9170, more or less. So to find that rate, we know that 1 plus the rate equals 0.9170. So we're going to subtract 1 from both sides. So that's going to give me negative 0.083 if I round. So the decay rate is 8.3%. Now they're asking us how much will remain after 10 days. So we aren't given any kind of amount. So if we think about it this way, if y equals a times 0.9170 to the 10, we can just take that 0.9170, raise that to the 10th power, That tells me I have 0.4204, so about 42%. Well, it's longer than the half-life, so we should have less than half. We can do this with a base E also if you care to. You got another step in the process to find that annual rate, so I don't think I'll show it to you here, but you can. So this question, they're telling us the half-life is 15. They want us to find the continuous decay rate, not the annual like we did in the last question. So to find the continuous decay rate, that's going to be e to the kt, right? A times e to the kt, that format, where there's a continuous growth. So let's see. We know the half-life is 1/2. Half-life is 15. So I know if this is equal to y, and I know y divided by a is 1/2, how much I have now divided by what I initially started with should be 1/2 if it's a half-life. So I can say 1/2 equals e to the k times 15. Well, to solve this equation, we're going to take the natural log of both sides because it's base e. So I get ln 1/2 equals 15k, so then I'm going to divide by 15, and that will be the continuous rate. So my calculator tells me when I do that calculation, negative 0.0462, so about 4.62%, and it's negative, is my decay rate, continuous decay rate. Then they want us to know how long until only 10% remains. Let's write a basic equation. Let's see, we have y equals a times e to the negative 0.0462t. And I know when y divided by a, that should be equal to 0.1, 1/10. So then to solve that, I'm going to take the natural log of both sides, because it is base e again. So that's going to give me the natural log of 0.1 equals negative 0.0462. So I'm going to grab my calculator, find that, divide it by that, and that will be how long until there's 10% left. So my calculator tells me that this is about 49.8384, I guess. So just under 50 days, or hours, whatever the unit is. So it is hours. So 49 to 50 hours. So this is the math that you're going to use in your life. Guaranteed. An account grows by 6% a year. It's compounded monthly. How long will it take to double in size? So this is a doubling situation. A lot of different ways to set it up. In order to keep it easy, let's just do this. So the balance in an account is determined by your initial principal times 1 plus your annual interest rate divided by how many times they are figuring your interest, raised to how many years you're leaving in the account times how many times each year they're paying the interest. So in this case, it compounded it monthly, so we've got some amount, they didn't tell us how much, equals 1 plus 0.06 divided by 12 raised to the 12t, because we don't know how long. Now, they didn't give us an amount, but what we do know is when I divide b by p, I better get 2 if it's doubled. So then I'm going to grab my calculator. I'm going to do 1 plus 0.06 divided by 12. I'm getting 1.005 raised to the 12t. So now we could ln both sides. We could log both sides. I'm going to write the log just because it's different. And because I am taking a logarithm, I can use that exponential property, that exponent property of logs, to bring the exponent down in front. I better write a log of 1.005. I've got too many parentheses there, but that's okay. So then you're going to divide that log 2 divided by log of that, and then we'll divide that answer by 12, and that should tell me the time. So my calculator tells me 11 point, let's see, need a pen, 11.581 years. So just, or months it is, so just under 12 months. So I'd probably have to wait the 12th month to have my money double. We're looking for that annual growth rate here. We know the doubling time. So I'm hoping you can see that if I have y equals ab to the x, and y, if I'm looking for the doubling time, y divided by a should be 2. I don't know b, but I know it doubles in 10 days. So that will work. So now to find that answer, I'm going to take the 10th root of 2. So we know that's 2 raised to the 0.1, or 1 divided by 10. That's supposed to be a 10. My calculator is telling me that's 1.0718. And remember, this is 1 plus r. So r has to be 0.0718, or about 7.2%. Since this isn't my open math, we can round a little bit. So that's my annual rate. How large will the population be in 20 days, 45 days? So they're going to refer to it, may have us refer to this as like in regards to the initial. So I've got an equation here that looks like this. I know that the population equals a times 1.0718 to the t. Well, for 20 days, I'm going to say a times 1.0718 to the 20. And for the 45, I'm going to say a equals 1.0718 to the 45. And those should be the two answers. It'll be in terms of a. This is the Newton's law of cooling problem, and there's all kinds of ways to set this up. I think what we want to keep in mind is it's just an exponential function. And what we can say is we can say the temperature currently depends on the time, a lot of t's, is a times e to the kt plus some surrounding temperature. And if you look in the book, this is kind of how they set it up. And then what we have is we have a couple of situations here. So turkey is taken out of the oven at 165 degrees. So at time 0, that turkey is 165 degrees. Okay, we know the surrounding temperature is 70, so we know that's going to be 70. We know 10 minutes later the turkey is 150 degrees. They're asking us to what's the temperature 30 degrees later. And then they're asking me how long to cool to 100 degrees. So we're going to set up an equation, then use it to find these two missing values. So I know at time 0, the temperature is 165, and I know right now that I can set this up, a e to the kt plus 70. So I guess I got to find a. Well, I know at time 0 it's 165. So 165 equals a e to the k times 0, right? Plus 70. So subtract 70, that's going to give me 95 degrees. Equals a times e to the 0, and e to the 0 is 1. So it looks like a is 95. So then I can set this up. I can use the second point to find k. I know the temperature is 150 degrees at time 10. Whoop, not A. I should be writing E. So now doing a little algebra. What is that? 80 equals 95 e to the 10k. So I'm going to divide by 95. And that gives me, let's see here. That gives me 0.84211 equals e to the 10k. So then I'm going to take the natural log of both sides. Now I didn't round on my calculator, so this might be slightly different than if you typed in 0.84221 or 211. negative 0.1717. Let's try this again. That gives me negative 0.1719 equals 10K. So then I'm going to divide by 10, and that'll give me a K value of 0.01719. So my equation is going to be the temperature based on the time equals 95 e to the negative 0.01719 t plus 70. So then to evaluate it, they want to know what's the temperature of the turkey 30 minutes later. So you're going to say what's t of 30 basically. So 95 e to the negative 0.01719 times 30 plus 70. Enter that in my calculator correctly. I got 126.723 degrees. Then we're going to have to solve this equation for the next part for when is it equal to 100. So when is 100 equal to 95 e to the negative 0.01719 t plus 70. Subtract 100. Divide by 95. So 30 divided by 95 is 0.31. Whoops, did this wrong. Wrote it wrong. Said it correctly, wrote it wrong. 0.3158 equals e to the negative 0.01719 t. So I'm going to take the natural log of both sides to get rid of the e. And then I'm going to divide that answer by the negative 0.1701 t. So if I did this arithmetic correctly on my calculator, I got 67.055 minutes, I think the time unit is. Did that make sense for what they've given us? So a little over an hour to cool off to 100 degrees. I guess so. I mean, I guess if you didn't cut it up, that would make sense. Let's see, 10 minutes it was 150. 30 minutes we said it was 126. And then another 30 minutes, 37 minutes. Seems a little long, but I don't see where my math is wrong. So it's similar kind of setup. We know the initial temperature is 85. After 30 minutes, it's down to 82. We know the surrounding temperature is 60. So I know that 85 equals A times E to the K times 0 plus the surrounding temperature, which is 60. So that tells me that 25 degrees is the A, or 25 is the A. And then we can say, if you use the other factoid here, 82 equals 25 e to the K times 30 plus 60. So that's going to give me 22 divided by 25 equals e to the 30K. So then I'm going to natural log, take the natural log of both sides. So let's see, the natural log of 22 divided by 25, and then I'm going to divide that answer by 30. That's telling me K equals negative 0.0043. And then when did the person die? And we're assuming when the normal body temperature is 98.6 degrees. So we want to know when is the temperature, at what time was the temperature 98.6 degrees, given that we have a 25 e to the negative 0.0043 t plus 60. So now the algebra we're going to do, I'm going to subtract 60, divide by 25, take the natural log of both sides, and then we're going to divide by that, and that should give me the t. So that's telling me that the time is negative 101.018. So this is telling me about 100 minutes ago, 101 minutes ago is when the murder happened, or when the person died. And a 60-degree temperature, yeah, I guess so.